Welcome. Today, we're going to jump into a calculus problem that, I gotta say, trips up so many people. It looks totally normal on the surface, like any other definite integral, but there's this little hidden trap inside that completely flips the answer on its head. Let's break it down together.
So, take a look at this. Seems pretty straightforward, doesn't it? Well, let's see if you can spot what's tricky about it before I get there. Go ahead and follow along as we work through it.
Okay, so let's just dive right into this. First, we're going to tackle it the way most of us would at first glance, just by applying the standard mechanical rules of integration. We'll find the antiderivative, plug in the limits, and see what number pops out.
The easiest way to do this is just to break it down, right? Term by term. That first one, 5t to the 6th, that integrates to 5t to the 7th over 7. That's just our classic power rule. The second term, minus 10t, becomes minus 5t squared. And that last piece, 1 over t, well, that integrates to the natural log of the absolute value of t. So far, so good, right? Nothing too crazy.
Okay, so when we stitch all those pieces back together, we get our complete antiderivative, f of t. You can almost think of this as our secret weapon for the next step. It's the key that's supposed to unlock the area under our original curve.
All right, now it's time to bring out the big guns, the fundamental theorem of calculus. So first things first, we're going to plug in our upper limit, which is 3, right into that function we just found. This gives us the value at the very end of our interval.
And then, you guessed it, we do the exact same thing for the lower limit, -2. And that absolute value on the natural log, yeah, that's super important here. Because, you can't take the log of a negative number. That's a big no-no in math.
Okay, so we've got our two values, we subtract the lower from the upper, and boom, we get a number, about 1628.98. And that feels good, right? It's clean, it's a solid number. Problem solved. Or is it?
But wait a second. Hold on. This is where the whole thing just gets fascinating. When you just follow the steps by rote, it's so easy to miss a detail, a really, really critical detail. What if that nice, clean number we just calculated is completely wrong?
So yeah, let's just put it right out there. Is that the real answer? Did just following the rules lead us to the right place, or did we just walk straight into a carefully laid mathematical trap?
And here it is. This is the catch. That little term, 1 over t, has a massive problem. It is completely undefined when t equals 0. This creates an infinite discontinuity, a vertical asymptote, and it's sitting right smack dab in the middle of our interval, from -2 to 3. Look, this isn't just some tiny little detail. This is a complete game changer. It basically invalidates the entire method we just used.
Now, what's really interesting about this slide is it shows you exactly why this matters so much. On one side, you've got a nice continuous function. Think of it like a perfectly paved highway. It's smooth, it's connected, no problems. But our function, it's more like a road with a giant bottomless canyon right in the middle of it at t equals 0. And here's the thing. The fundamental theorem of calculus, it's designed for those smooth highways. It just doesn't work when there's a huge break like that. The whole idea of finding the area kind of falls apart when parts of that area shoots off to infinity.
So that one little point, t equals 0, it changes literally everything. We thought we were calculating a simple area, but we're actually dealing with a totally different beast now.
And that brings us to the real name for this kind of problem. This isn't just a regular old definite integral. This, my friends, is an improper integral. And when you see that term, it should be like a big red flag waving, telling you to slow down and think critically.
So what does that mean for our answer? Well, because that function basically blows up at t equals 0, it shoots off towards positive and negative infinity, the area we're trying to measure is technically infinite. That's the real answer here. The integral diverges. It doesn't land on one specific number because the area is just endless.
So what is the big takeaway from all this? It really boils down to this crucial difference between just blindly following a procedure versus actually understanding what's going on underneath.
And this table just lays it all out so clearly. On one hand, you've got the procedural answer, that's 1628.98. It's a number, sure, but it's built on a faulty assumption that the function is continuous. On the other hand, you have the actual, theoretical reality. The integral diverges. This isn't a number, it's a conclusion that the area is infinite, and it acknowledges the massive discontinuity we found. One is just a number from a recipe, the other is the truth.
So, the golden rule, the thing you have to remember from this, is simple but so powerful. Always, and I mean always, check for those discontinuities in your interval before you even start integrating. It's just a great reminder to never take the setup for granted. And that leaves us with